A radio transmission system demonstrates one way of transmitting electrical energy and converting it into another form of energy, radio waves. Its function is not unlike the method of converting electrical into light waves. A fan converts electrical energy into mechanical energy, which results in the movement of air. In each case, the energy has to be transmitted from a power source to the fan, to the or to the antenna. Here is a tabletop demonstration of a complete antenna system. A transmitter transmits radio waves along two wires to the antenna. The two wires of the transmission line have a job similar to the transmission line of the fan on the desk or the light. Transmission lines, then, are basically two parallel wires. Let's dream up a theoretical transmission line and study its behavior. The two wires will be endless or infinite in length. Now let's connect a source of electrical energy at some point. Even with our switch open, we know a voltage exists between the terminals of the battery and up to the open switch. Now, since this transmission line consists of two wires insulated from each other, they act in effect as a capacitor, or for that matter, as a series of minute capacitors. When we close the switch, battery current charges the beginning of the line, or the first capacitor. As current continues to flow from the battery, successive portions of the line become charged. This is a slow-motion illustration of the phenomena of electricity. Actually, this progressive charging of the line occurs almost instantaneously. When current moves along a line, magnetic lines of force are set up. On our theoretical line, we'll slow the current down to a walk and watch the buildup of magnetic fields. Let's hold the current right here. Notice how the magnetic fields have built up to a maximum size. The fields around the upper and lower conductors oppose each other. Notice that where you have maximum current flow or magnetic buildup, you have maximum voltage. The line would be charged progressively regardless of length. This characteristic of transmission lines remains the same whether DC or AC is applied. Let's use a source of alternating current in place of the battery. When alternating current is generated, the polarity at the generator terminals changes at each half cycle. Let's continue this slow motion, and this time watch the buildup of magnetic fields. The generator will turn one half cycle. The maximum magnetic field is produced at the quarter cycle point, because it is here that the generator is cutting the greatest number of flux lines. As in our demonstration with direct current, the magnetic fields cause this portion of the line to be charged to the voltage of the generator. Now let's continue the slow motion action to see what happens to this electrical charge on the wires. Even with the generator stopped, this single charge proceeds down the transmission line. Letting our generator run, we see the actual wave motion of electrical energy produced along the line by an AC generator. This represents the electrical energy produced by one complete cycle of the generator. It is one wavelength, or the measurement of the distance traveled by the electric impulse during one cycle of the generator. Since this shows electrical energy composed of fields in motion, it is but a short step further to plot a current graph from the magnetic field and a voltage graph from the voltage field. Notice that the current and voltage plots are a direct measurement of the strength of the field. As you can see for yourself, the current and voltage match in amplitude. Whenever this occurs, the current and voltage are said to be in phase. Now, since current and voltage are in phase, our transmission line is acting as a resistance. This resistance is called the characteristic impedance of the transmission line. To the generator, characteristic impedance appears the same as any resistor of equal value placed between the generator terminals. If the characteristic impedance of our infinite line is 600 ohms, we could terminate the line with a 600 ohm resistor. We have changed our infinite line into a practical line, yet the resistance and current remain the same. No matter where the line is cut and the resistance inserted, the line still presents the same characteristics, voltage and current remaining in phase. Because it behaves the same to all frequencies, we call this type of line non-resonant. Our alternating current patterns still look the same, although the infinite line has been changed into a practical line. For a simpler demonstration, let's use a single part of the pattern, in this case, the voltage field. And since it is easier yet to use the sine wave of the voltage, we can represent the voltage field by a voltage sine wave. Here the sine wave indicates the alternating current in the line. The energy that hitherto charged the infinite line is now being dissipated by the resistor in the form of heat. To put it another way, the energy of the electric field has changed to heat energy. This would not be the case if we were to change the value of the resistance across the line, say from 600 ohms to 1200 ohms. Now the resistance across the line does not match the characteristic impedance, and so we have a resonant line. When this mismatching occurs, some of the energy is reflected back down the line. The resistor does not dissipate all of the electrical energy applied to it. Reflection always occurs whenever the resistance across the line is greater or smaller than the characteristic impedance of the line. The wave leaving the source of power is called the incident wave. The returning wave is called the reflected wave. The amplitude of reflected waves vary. In this case, the resistance is not much greater than the characteristic impedance. Therefore, the amplitude of the reflected wave is comparatively small. As the resistance is increased, the amplitude of the reflected wave increases. If the resistance across the line is just a bit less than the characteristic impedance, the reflected wave will again be small in comparison. And as the resistance value is further diminished, the wave again increases in size. Since reflected waves become greater as the difference between R and Z sub O becomes greater, a closed transmission line can be used to achieve maximum reflection. The shorted end of the line offers zero resistance and generates no heat. Mismatch of Z sub O and R is at a maximum, and the reflected wave reaches maximum amplitude. An open-ended line achieves the same result. The open ends of the circuit offer maximum resistance to the passage of current. There is no power dissipation. The incident wave simply bounces back at the end of the line to become a reflected wave of maximum amplitude. Using this table model of a closed-end transmission line, let's imagine the incident and reflected waves are visible, in slow motion, of course. In this closed line, the incident and reflected waves are of equal amplitude. Now here's another phenomena of resonant transmission lines. When an ordinary fluorescent lamp is placed near the line, it can be used as a voltage indicator. When the tube glows the brightest, it indicates a point of peak voltage in the line. A voltage plot of this line would look like this. But you may point out, how can the voltage values remain constant when the radio waves shift continuously? Well, it's the phenomena of the standing wave. The standing wave is produced by the action of the waves moving in opposite directions. It is a very convenient miracle because it will stand still to be measured. If a zero-center reading voltmeter could be designed to read this electrical phenomena, it would give the same indication as the voltage plot, the same indication as a fluorescent lamp, which reacts to voltage. The rise and fall of voltage and current follows the standing wave. Remember, this standing wave is not a physical thing, but rather the resultant values of the combined incident and reflected waves at any point along the line. For instance, let's stop the traveling waves. Now we can measure the amplitude of the incident and reflected waves at any point. At the first point selected, the top arrow measuring the positive amplitude is equal in length to the bottom arrow measuring negative amplitude. By projecting our amplitude measurements on the plot of the standing wave, we find that the negative and positive amplitudes cancel each other, resulting in a zero reading at this point. At our second measuring point, both curves are above the reference line showing positive amplitude. When both arrows are added together, their combined length again equals the exact amplitude of the standing wave at the corresponding point. At the third point, both curves are below the reference line, showing negative amplitude. The combined length of the two arrows again measures exactly the amplitude of the standing wave. Starting and stopping the waves again, we discover a different set of values for the standing wave. Only the zero amplitude points remain constant, or just on the reference line. However, the amplitude at all other points has changed. Shifting our waves once again, our new measurements show that the positive and negative arrows cancel each other at all points along the waves, giving us a constant zero reading that follows the reference line. With 3 readings, we've gotten 3 sets of values for one standing wave. A measuring of all possible values of the standing wave will give us a picture of the varying values that exist between the constant zero points. The reading of the standing wave you will get with a current or voltage indicator is the effective value of these many curves. This value, of course, remains constant. The standing wave of current on the transmission line can be plotted as easily as the voltage. It is a closed circuit. At the shorted end, the current reading is maximum for the line. A half wavelength down, the current is again maximum, and so on to complete the standing wave of current. The voltage at the closed end of the line is, of course, at minimum value. 1/4 wavelength down, the voltage reaches its peak, and so on to complete the standing wave of voltage. Impedance is minimum at the shorted end of the line. According to Ohm's law, when current is maximum and voltage minimum, the impedance is minimum. In the case of an open-ended transmission line, we find an immediate difference in the current curve. There is no current flow at the open ends of the line. Therefore, the current curve is at low point here. Voltage at the open ends of the line is at peak point. Impedance at the open end is maximum. With the same frequency applied, a comparison of the shorted and open line shows that the curve values are reversed. How does this apply to radio antennas? Well, let's shorten our closed-end line and find out. Now we're working with only a 1/4 wavelength of a closed transmission line. The impedance at the terminals of the generator is maximum. In other words, the generator sees the circuit as one of maximum impedance. Where a line presents a high impedance to the generator, it is the same to the generator as though it were connected to a parallel resonant circuit. So we can symbolize this 1/4 wavelength line as a parallel resonant circuit. Connected at the half wavelength point, the generator now sees a different condition. Impedance is low, and where a line presents a low impedance to the generator, it is the same as if a series resonant circuit were connected to the generator. At the 3/4 wavelength mark, the impedance is again at maximum, and again the generator sees a parallel resonant circuit. At the 1 wavelength mark, the generator sees the circuit as a series resonant one. The behavior of our open line can be investigated in the same manner. At the 1/4 wavelength point, the generator sees a condition of minimum impedance. This circuit can then be considered a series resonant circuit. Each time a 1/4 wavelength is added to the circuit, the condition changes. Thus, open and closed end lines can be used as parallel or series resonant circuits. according to the length of line used. Because of this facility, they are known as resonant lines or tuned lines. In this quarter wavelength of open transmission line, we have the requirements for a radio antenna. Let's take a quick look at the electric field here. Because the current flows in opposite directions in the two conductors, the directions of the magnetic fields are opposite, and any radiation is canceled. How can we use this device as an antenna? Very simple. We spread the wires apart. Presto, a dipole antenna. Notice that the current flow is in the same direction in both conductors, or in other words, the same in both halves of the antenna. The direction of the magnetic fields is now the same, and instead of opposing each other, they strengthen each other. This is your basic antenna. It is called the half-wave dipole antenna. Our tabletop antenna system uses a half-wave antenna. Let's examine the kind of radio waves it sends out. The vertical rings represent the magnetic lines. The horizontal rings, the electrostatic lines. Let's say these lines form a single wave, and we'll stick with this wavefront as it is radiated into space. Upon leaving the antenna, the pattern enlarges. It stretches, yet the magnetic and voltage lines retain a fixed relation to each other and to the Earth. For instance, stopping the wave, we see that the magnetic or H lines are still perpendicular to the voltage or E lines. Also, we see that the E lines in this wavefront remain horizontal or parallel to the Earth's surface. Because of the direction of the E lines, we say that this wavefront is horizontally polarized. In order for a signal to be received at maximum intensity from this wave, the H lines of the wavefront must cut the receiving antenna at right angles. Therefore, the polarization of the receiving antenna must also be considered. In this case, the receiving antenna must be horizontal and at right angles to the H lines of the wavefront. The transmitting and receiving antennas are now parallel and broadside to each other. This broadside position is necessary because of the nature of the radiation pattern of the half-wave antenna. The shape of this pattern indicates areas of no radiation or nulls along the axis of the antenna. A receiving antenna placed in a null area would be unable to receive a readable signal. Moving the receiving antenna into the radiation field, it will start to pick up signals that increase to maximum strength when the receiving antenna is broadside to the transmitting antenna. By plotting a graph of the signal strength received, we get a cross-sectional view of the radiation pattern. A three-dimensional representation of the pattern looks something like a donut. Regardless of its physical length, any half-wave antenna will radiate this type of pattern. A half-wave antenna should measure half the wavelength of the frequency employed. This broadcast antenna measures approximately 309 feet. It operates on a frequency of 1590 kilocycles, corresponding to a wavelength of about 618 feet, or twice the length of the antenna. As radio frequencies decrease, wavelengths increase, and the length of the antenna must increase, so that some radio frequencies would require a half-wave antenna too big to be practical. What can we do about this? Well, the same quarter-wave transmission line holds a few more tricks up its insulation. When only one wire is moved perpendicular to the other, the closed electric field which existed between the upper and lower conductor becomes a partially open field. Since the lower conductor is grounded, similar electric fields occur all around the upright conductor. Our upright conductor now functions as an antenna, a quarter-wave antenna. The quarter-wave transmission line with one conductor upright is quickly changed into a practical antenna system. The ground takes the place of the lower conductor. The upright conductor becomes an antenna tower. Our source of power becomes a transmitter, which is located some distance from the tower to prevent distortion of radiation patterns. The efficiency of a quarter-wave antenna depends largely on the nature of the ground. At installations near the sea or in salt marshland, the Earth's conductivity is excellent, and a simple metal stake provides proper ground. In drier regions, a system of conductors installed at the base of the tower may be required. These radial conductors are connected to a common point at the base of the tower. Sometimes on some installations, an additional system of wires lying on the ground called a ground screen is used, thus forming a more effective ground. Where it is not practical to bury conductors, a network of wires called a counterpoise is built above and insulated from the ground. A transmission line transfers power to the antenna, and herein lies a final problem. Matching the impedance of the transmission line to the input impedance of the antenna in order to eliminate reflection and obtain maximum power transfer. Remember the impedance curve on our quarter-wave transmission line? Watch what happens to the impedance curve when we make a half-wave antenna out of this line. The general shape of the curve is the same. Impedance is still maximum at the ends of the line and minimum at the center. There is a given value in ohms for this point of minimum impedance, 72 ohms. How do we arrive at that figure? Well, we know that when our antenna is radiating, it is dissipating energy. Tests show that the amount of energy radiated by the antenna is equivalent to the heat energy dissipated by a 72 ohm resistor connected across the generator terminals. At the ends of the antenna, impedance has a constant value of approximately 2400 ohms. With known values at the minimum and maximum points, we can interpolate values at any point on the curve. Now we can match the antenna and transmission line in impedance. Let's say that the characteristic impedance of the transmission line is 600 ohms. If this is the case, our transmission line is connected to the antenna at the wrong point. 600 ohms does not match 72 ohms input impedance at the center of the antenna. When power is applied, there will be some reflection because of this mismatch of impedance. To match impedance and thereby get maximum power transfer, we simply spread the ends of the conductors apart, connecting them at matching points of impedance on the antenna. Now there is no reflection. We get maximum power transfer, maximum radiation. This system of impedance matching is called the delta match. Another method of impedance matching employs two lengths of metal tubing called a quarter-wave matching transformer, or Q-bars. These tubes are merely the twin wires of our old friend, the quarter-wavelength resonant line. In this sample closed line, the impedance curve is minimum at the closed end and maximum at the other. Now, supposing we put a resistor in the closed end of the line, say 72 ohms. Now we know that our impedance value at this point is 72 ohms. This changes our curve a bit, decreasing the impedance value at the generator end of the line because the standing wave is no longer at maximum amplitude. Now let's bring our antenna into the picture again, connecting it to the closed end of the line and removing the resistor. As the characteristic impedance of the transmission line is 600 ohms, it remains for us to match this value at the junction with the quarter wavelength line. We can get this matching value by simply shifting the Q-bars closer together or further apart, thus changing the impedance until we find a value to match 600 ohms. Once this value is found, impedance matching is completed, and we can look for maximum radiation from our antenna. There's still another way to match the characteristic impedance of a transmission line to the antenna. This method is called stub matching. Let's say we're given a transmission line with a characteristic impedance of 600 ohms. We know that a matching value in ohms can be found at some point along the length of the stub. Let's start looking. This hookup gives us some reflection, meaning a mismatch of impedance values and a consequent loss of power. So, we'll slide our line along the stub until we find the point of matching impedance. The radiation of the antenna can be checked. When maximum radiation occurs, the position of matching impedance has been found. Thus, we have demonstrated a basic requirement for a system that will convert electrical energy into radio waves. Such a system would use a transmitter, a non-resonant transmission line, an impedance matching device, and an antenna. These are the fundamentals of a radio antenna system.